In Section 2 of Unit 6, we are going to examine the idea of preservation of equality, and we will do this with each of the four main operations: addition, subtraction, multiplication, and division. We will use models including a two-pan balance and algebra tiles for this purpose. Lesson 1 of Section 2 will focus on the operation of addition in the preservation of equality. So recall that the purpose of an equal sign is not just to indicate an answer. It is a symbol indicating that something is the same as another. It is equivalent. It is balanced. Throughout the remainder of this unit, whether solving equations using modeling or symbolically, you will repeatedly hear, whatever you do to one side of the equation, you must do to the other. And this is a very important concept when solving equations. As we delve into the preservation of equality concept, and we look at addition first of all, we're going to consider our two-pan balance. We'll use that model first. And we need to remember that whatever I add to one side, I must add to the other. That will maintain balance. So let's look at our balance scales. Here's our two-pan balance. And first of all, on the left-hand side, we've placed a mass of 12. And on the right-hand side, we've placed two 5 masses and a 2. We know that 12 equals 5 plus 5 plus 2. That's why our two-pan balance is level here. It's balanced out. However, if I add a mass of 8 to the left, you obviously see that that left-hand side now has more mass. It is no longer balanced with the right-hand side. 12 plus 8 does not equal 5 plus 5 plus 2. To maintain the balance, well, what do I need to do? There it is. We need to put a mass of 8 on the right-hand side. And of course, 12 plus 8 does indeed equal 5 plus 5 plus 2 plus 8. So when I added a mass of 8 to the left-hand side, I had to add a mass of 8 to the right-hand side to keep it balanced. Let's look at another example. This one is a linear equation. It has a variable thrown in. Here's our two-pan balance. So on the left-hand side, we're going to represent x plus 3. And on the right-hand side, we have our 7. So LHS for left-hand side, RHS for right-hand side. For the left-hand side, I'm going to use a hexagon with an x put in it to represent our variable, then a mass of 3, and on the right-hand side, we have our mass of 7. If a mass of 5 is added to one side, obviously it's going to tilt down on the left-hand side. More mass has been added. What do we need to do to balance it out? Well, of course, to maintain balance, a mass of 5 must be added to the right-hand side. The equivalent equation will become x plus 3 plus 5, that's what we have on the left, equals 7 plus 5, that's what we have on the right. And we can combine. We know that 3 plus 5 is an 8, and 7 plus 5 is 12. So x plus 8 equals 12. This would be an equivalent equation to what we started with, x plus 3 equals 7. Keep in mind here, we are not solving anything. We are not finding x. We're not finding our solution. We are just creating equivalent equations. Let's have a look at our second model now, that being algebra tiles. And still, whatever we add to one side, to maintain balance, we must add it to the other. With algebra tiles, we have what's called a variable tile. And that could represent 1x or 1n or 1m or whatever other variable you've used. And we have what's called a unit tile. And that just represents 1, a positive 1 in this case. If we have 2m plus 3 equals 5, and we're going to represent, then on the left-hand side, I have 2 variable tiles to represent the 2m, and I have 3 unit tiles to represent the positive 3. So that's on the left-hand side. On the right-hand side, I have my 5 unit tiles to represent a 5. We are going to create an equivalent equation by adding 2 unit tiles to each side. So let's have a look. So there's my representation again. Now let's add in 2 unit tiles to both sides. There we go. Symbolically, we now have 2m plus the 3 that we had before and the 2 new ones. So that's on the left-hand side, 2m plus 3 plus 2. And on the right-hand side, we have the 5 that we had there originally and the 2 that we just added in. We can simplify this a little bit to give us 2m plus 5 equals 7. We have a total of 5 unit tiles now on the left-hand side and a total of 7 unit tiles on the right-hand side. So 2m plus 5 equals 7 is an equivalent equation to what we started with, which was 2m plus 3 equals 5. One more example. 4 equals 1 plus 3n. So let's represent, first of all, using our algebra tiles. On the left-hand side, 4 unit tiles. On the right-hand side, we see 1 unit tile and 3 variable tiles. Now, what are we going to add into both sides this time? We're going to add in 1 variable tile and 3 unit tiles to each side of our equation. There's the original representation. Now let's add in our 1 variable tile and 3 unit tiles to each side. So what have we got now in total? Well, on the left-hand side now, I have 1 variable tile corresponding to the 1n. I have 3 new unit tiles, as well as the 4 that were already existing there on the left-hand side. On the right-hand side, we have the 1 unit tile that was already there, the 3 variable tiles that were already there, and now we have this 1 new variable tile for the 1n and 3 new unit tiles. We can combine, we can simplify here. So I have 1n plus 7 equals 4n plus 4. n plus 7 equals 4n plus 4. That would be an equivalent equation to what we started with. If we were to solve, the solution that you would get for 4 equals 1 plus 3n would be the exact same value that would satisfy n plus 7 equals 4n plus 4. Your solution would be the same because the equations are equivalent. And now I'd like you to proceed to the next video in this lesson.